This conference will now be recorded.
Okay, we can start. That is, we have discussed something regarding that channel coding in the last session, and we have defined what is meant by that important type, that classification, block code and convolutional code, linear code and uh, non-linear code, and also forward acting sorry, code with forward acting error correction and error detection with the transmission, like that, some classifications like that. Then some definitions, what is meant by a code word, block length, code rate, and hamming distance and minimum distance. This have we have discussed in the last class. Okay, then now we can go to the linear block code. Here, linear block code means it satisfies that condition for that block code, and also that linearity property satisfied. In block code, we are taking the message together, and it generate a block of code. In general, we can say NK block code. NK block code. Here, K message bits are taken, and corresponding to each K message bit, we are generating a N bit code word. That is, the length of that code word is N. That is, we are adding extra bit, which is termed as uh, check bits, or we are adding that redundant bits for the purpose of error detection and error correction. Okay. Then here we can say uh, and that linearity property means that sum of two code words give another code word. Sum of two code word give another code word. That is when by that linear code. And here we can say the message block input. A block of message is given to the channel encoder and code block output. That is that code word as a block. And here we can say K message bit. That message is we are taking is K bit length, and the output is N bit. And uh, in that message, K message bit, and also that check bits, N minus K number of that K N minus K number of check bits, extra bits there. Okay, N minus K message bits. That is in that NK block code, K message bits are given as the input, and in the final code word corresponding to that K message bit, K bit will be message bit, and the N minus K bit will be the check bits. Okay, and here this linear block code uh, are of two types: systematic code and non-systematic code. In systematic code, the message bits appear at the beginning of the code word. That is here, that is actually that here this representation. That is, initial part of that n bit code word will be that message itself. Then after that message bit, the check bits, that is n minus k bits. Sometimes we take the represent that n minus k by the letter q. That is q number of check bits we are using. Q number of check bits we are using. That is that n minus k is equal to q. That is in systematic code, out of that n bit code word, initial part will be the k message bits, and the next n minus k or q number of check bits. Then we say it is a systematic linear block code. That is linear block code. In systematic code, the message bits appear at the beginning of the code word. And in non-systematic code, it is not possible to identify the message bits and the check bits. That is in a mixed manner. That is total corresponding to that k message bits, we are generating n bit code word. That is out of that n bit code word, that message bits and the redundant bits, check bits are in a mixed manner. That is, we are not able to possible to separate that identify that message bits and the check bits once the code word is generated. For that, linear block code is of two types: uh, systematic code and the non-systematic code. Systematic code and the non-systematic code. Okay. Then we can consider we have already defined that a code is linear if the sum of any two code vectors produces another code vectors. This if there are four messages and we are generating four code word corresponding to each k bit message, we are generating n bit length code word. And if we out of that four code word corresponding to that four message bits, message sequences, if we take two code word, then if we add that code word together, it will be another code word. That is that linearity property. A code is linear if the sum of any two code word produces another code vector. Okay. We can take consider m1, m2, etc. mk are the message bits. It is usually we denote that message bits as m1, m2, m3, etc. up to mk. That is k message bits. And c1, c2, etc. up to cq. Here that q is equal to n minus k. Okay. C1, C2, etc. Q, that small letter q is equal to n minus k. N minus k, that is the q number of check bits, n minus k. Therefore, the code vector, that code word can be written as, usually it is represented by the letter x, x equal to m1, m2, etc. mk, then c1, c2, etc. cq. That is, if it is a 3-bit message, then 1110, if these are the message bits 1110, then corresponding to that check bits obtained as 001, that is c1, c2, c3 we have obtained as 001. Then that complete code word is, initial part is that message 111110, then 001, like that. That is corresponding to each message bits, k message bits. That is, here we have represented it as m1, m2, etc. mk. And corresponding to that, we have generated the check bits c1, c2, cq. Then the complete code word, that n bit code word is m1, m2, etc. mk. Then write that c1, c2, etc. cq. That is, here it is, we are discussing that systematic linear block code. That is, here that q is equal to n minus k. This we can represent like this, that x equal to x, here represent the code word. Initial part is that message bits, here m, capital M represent that message sequence, and that is k number of message bits, and c, capital C represent that check bits, that extra bits we have added. And here this check bits play the role of error detection and correction. We will see how it is detecting that error, and how it is we can make use of that the check bits for the error correction. Anyway, that is, in this channel coding we are generating that purpose is that error, it is known as error control coding. Reason is we are adding redundant bits, extra bits, which is termed as check bits, and it is used for the purpose of error detection and the correction. Okay, then here that code vector can be represented as okay. Next, it is important. It is corresponding to each linear block code. There
This conference will now be recorded.
okay. Hope that I am audible. If there is any problem, can I continue? Please say yes or no. Please respond through the chat in between a call receiver. Please say someone.
Yes, sir, you're audible.
Okay, thank you. Okay, here linear block code. Associated with each linear block code, there exists a matrix which is represented by the letter G, capital G. G is termed as a generator matrix. And we can obtain the code word X by multiplying that message with the generator matrix. Therefore, it is represented as X equal to M into G. This here, this X is the code word, and M is the we can represent as a matrix, a row matrix. That is, if it is a 4-bit message, then 1110. An example, it is represented in a row. Therefore, then that message multiplied with the generator matrix gives the code word corresponding to that particular message. Therefore, if there are that k is equal to 3, number of message bits equal to 3, then we can have 8 possible message combination. Then in order to generate that code word can be obtained by multiplying, taking each message and multiply with that generator matrix. That generator matrix is specific to a particular code. That is, by making use of that generator matrix, we are generating the code word. Therefore, it is with different generator matrix, we are generating different code word. For a particular generator matrix, it generates a set of code word. Okay, anyway, that X equal to M into G. Okay, code word can be obtained by multiplying that message matrix with that generator matrix. That is, message is represented as a matrix, is a row matrix. Then that is here X equal to code vector of 1 by n size. Okay, the size of that matrix can be written as 1 by n. Then message will be of the size 1 by k, the order of that matrix. If we consider that message matrix, then 1 by k is the order of that matrix, the size of this vector. Then generator matrix has the order k by n. Okay, that is, in order to generate a linear block code, that we are making use of that generator matrix. Okay, it will in exam point of view, the generator matrix will be given, and by making use of that, we are generating the code word. Okay, and the same generator matrix, we make use of that for the decoding purpose. Okay, anyway, here note that X equal to M into G, that code word can be obtained by multiplying the message with the generator matrix, and the generator matrix is of the order k by n. Then here that generator matrix, the general form of this generator matrix is initial part ik, that is a kth order identity matrix. That is, the generator matrix have of the general form. Initial part will be an identity matrix of the kth order. We know what is that k denotes. Then the remaining part, that is, here we know the order size of the generator matrix is k by n. Okay, k by n is the order of the generator matrix. Therefore, initial part is k, then the remaining part will be a matrix of the order k by q. Here that q is equal to n minus k. I hope that clear. That is, the generator matrix is of the order k by n. Generator matrix is of the order k by n. For every generator matrix, the initial part is an identity matrix of the order k. That is, if it is a 7-3, we are generating a 7-3 block code, 7-3 block code. Then the order of the generator matrix is 3 by 7, nk 7-3. Okay, we are generating a nk linear block code. For example, take it as 7-3 block code. Then the order of the generator matrix will be 3 by 7. And out of that generator matrix, the initial part will be an identity matrix. Therefore, it is a third order identity matrix. For it will be 1 0 0 0 1 1 0 0 1. That will be the initial part of that generator matrix. Then there is a matrix. Its order will be, if we separate that remaining part, that other than that identity matrix, then its order will be k by q. That is, if it is 7-3, then we can say 3 by 4 will be that order of that submatrix. Okay, and it is usually termed as p submatrix. Therefore, it is represented as p k by q. The point is, associated with each linear block code, there exists a generator matrix. We are making use of the generator matrix for generating the code word. We can obtain that code word as x equal to m into g by simply multiplying the message vector with the message generator matrix. And its general structure is, initial part is an identity matrix of the order k and a p submatrix, and its order is k by q. Okay, ik a k by k identity matrix, and p is a k by q submatrix. And earlier we said that x equal to m into g. Similarly, check vector, that extra bits we are adding to that message bits, we can say it is a check vector. That is, if it is a 7-3 block code, corresponding to each 3 message bit, we are generating 4 extra bits. For corresponding to each message, there exists a check vector of a length 4 that can be obtained c equal to m into p. That is, by multiplying that message vector with the p submatrix, we get that check vector. It is by simply multiplying that message sequence represented as a row matrix into the p submatrix, we get the check bits. If it is a 7-3 block code, take 3 message bits, then multiply with the p submatrix, it give 4 check bits corresponding to that 3 message bits. It will be clear when doing an example. Anyway, x equal to m into g, similarly c equal to m into p. Okay, you can take this problem. Hope that you are following. We can consider a problem. Here, generator matrix for a 6-3 block code is given. Find all the code vectors. Our aim is to write all the code vectors. Okay, please chat all of you. Can we go with this problem? Then the response on the end. Please type yes in the chat box. I want more responses. Okay. Okay. Here, note this generator matrix. That is, generator matrix is given 1 0 0 0 1 1 0 1 0 1 0 1 0 0 1 1 1 0. That is, here 6 3 block code, a linear block code, 6 3 block code. Therefore, here the order of the matrix will be 3 by 6. Here the generator matrix, you will have to remember that order of a generator matrix is k by n. Therefore 3 by 6, here the order of the generator matrix. It is given. We will have to generate the code vectors, code word corresponding to all the possible messages. Okay, note this k. Yes, generator matrix 1 0 0 0 1 1 0 1 0 1 0 1 0 0 1 1 1 0. Here we can see the initial part. Here this initial part, here it is a identity matrix. This part here we have an identity matrix 1 0 0 0 1 0 0 0 1. That is a third order identity matrix. Therefore, here it is the that remaining part. It is the P submatrix of this generator matrix. Okay, P submatrix of the generator matrix here. 0 1 1 1 0 1 1 1 0. It is the P submatrix. Here K is equal to 3. Here Q is equal to 3. That is n minus K. N is equal to 6. Then P is, we have this 0 1 1 1 0 1 1 1 0. It is the P submatrix we have. Okay. Here we have that linear block code P is equal to 0 1 1 1 0 1 1 1 0, and we can do the problem by generate the code vectors by multiplying that message vector. Here the different message vectors are 0 0 0 0 0 1 0 1 0 up to 1 1 1. By taking all the messages and multiplying with the generator matrix, which is a 3 by 6 matrix, by multiplying we obtain code word corresponding to each message. And another way we can do by making use of that C equal to MP, that is check vector, can be obtained by multiplying the message vector with the P submatrix. Therefore, here we can write here 6 3. Therefore, that Q is equal to 3. Therefore, we will obtain 3 bits, 3 check bits corresponding to each message bits. It is M1 M2 M3 C1 C2 C3. These are the complete code word. Here we are discussing a systematic code. Initial part 3 for a 6 3 linear block code, 3 message bits, then C1 C2 C3 the check bits. Therefore, we can write that C1 C2 C3 equal to M1 M2 M3 into that P submatrix. Okay, here this M1 M2 M3 8 possible combination. Therefore, initially we can write the expression for each check bit C1, C2, C3 in terms of that message bit by making use of this expression C equal to M into P, M1, M2, M3 into P. Therefore, multiplying M1 into 0, M2 into 1 plus M3 into 1. That is, here actually we are using that mode 2 addition. That is 0 plus 0 0 0 plus 1 1 1 plus 0 1 1 plus 1 0. Therefore, that is why it is represented like this addition, that XOR addition we are doing, mode 2 arithmetic. Therefore, we can obtain the equation for that check bit C1 equal to M2 plus M3. Reading it as plus, actually it is that mode 2 addition XOR, or we can say C2 C1 equal to M2 XOR M3. So then similarly C2 we can obtain M1 into 1 plus M2 into 0 plus M3 into 1. Therefore, C2 equal to M1 XOR M3. Then C3 equal to m1 into 1 plus m2 into 1 plus m3 into 0. Therefore, the C3 equal to m1 XOR m2. Okay, hope that you have understood how we have wrote the equation for each check bits. That is, now by making use of that P submatrix, we have written the equation for each check bits in terms of message bits. And earlier said that the generator matrix will be given for linear block code. In some cases, you will be asked uh, the check bits equation for the check bits will be given like this, that is c1 equal to m2 plus m3, c2 equal to m1 plus m3, like this. These check bits will be given and you will be asked to write the p submatrix, generator matrix, etc. This for a 6-3 generate for a 6-3 linear block code, the check bits are given. These three equations will be given, then you will be asked to write the generator matrix. Therefore, it is possible. C1 we have this C equal to m into p. Therefore, from this we can write the p submatrix. Then the generator matrix, we know the initial part is an identity matrix of the order k. Therefore, if the check bits equation for the check bits are given and if you are asked to write the generator matrix, it is possible. Okay, now here the generator matrix is given and the from that p matrix we have separated and we have written the equation for the check bits. Okay, next. Here you can for a particular problem you will have to do the problem like this. Initially generator matrix, we have separated the p submatrix, then written the equation for check bits c1 c2 c3. Then you will have to write the code word. For that it is better to prepare a table like this. All of you write the table like this, that is m1 m2 m3. Initial part is message bit. Here a message bit, please correct this. And here the message bits for m1 m2 m3, different possible combinations 0 0 0 0 0 1 0 1 0 etc up to 1 1 1. Then we will have to write the check bits by using the equation m2 plus m3. We have the check bit m here m2 plus m3, m1 plus m3, m1 plus m2. Therefore, here for the check bits corresponding to the message 0 0 0, here you can write this c1 equal to m2 plus m3. Therefore, 0 plus 0 0. Then c2 we have m1 plus m3. It is also 0 plus 0. Therefore, 0 c3 m1 plus m2 0. Then coming to the next message bits 0 c1 we have m2 plus m3. Better thing is you write here this ഈ table തന്നെ എഴുതുക. c1 equal to m2 plus m3, c2 equal to m1 plus m3, c3 equal to m1 plus m2. Then it is easy to complete this table. Therefore, we have c1 is m2 plus m3. Therefore, 0 plus 1, that is written here 1. Then c2 is equal to m1 plus m3. Therefore, 0 plus 1. Therefore, it is 1. Then m1 plus m2, that is that c3. m1 plus m3. Therefore, it is 1. Like that, all of you please complete this check bits.
This
It is
conference
here
will now be recorded.
that final column represent the weight of the code. It is the number of ones in each code word. Therefore, we can calculate the weight of the code. Here, if all the 6 bits are 1, then the weight of the code will be 6, like that. Anyway, we are able to write the weight of the code. Okay, then a d minimum equal to this, we can write that d minimum, have the d minimum that is minimum weight of the code where x is not a complete zero vector. It is equal to, we can write like this, weight of the code, x is the code word here, then its minimum value, where x is not equal to, symbol, okay, here not equal to that complete zero vector, that is here, that is the definition. Here you can write x is not equal to. Therefore, in this example, here d minimum, that minimum distance of this particular linear block code is consider the weight of the code. Out of this, avoid this particular one, that is for a complete zero code the weight will be 0. Other than that, the different weights are 3, 3, 4, like that. Out of this, its minimum value. Therefore, here 3 is the minimum distance of this particular block code. Here the minimum value of this weight is other than where x is not a all zero code, then here we have that minimum distance equal to 3 here. Okay, that is the one easy method to find the minimum distance, d minimum of a code. This find all the weight of the each code, then the minimum value of that weight where x is not a all zero code. In this example, avoid this particular weight, here it is 0, then consider the all the remaining weights. Out of this, which is the minimum value, that will be the d minimum distance of the code. Then significance of this minimum distance, we can say up to s errors, I'm saying up to s errors can be obtained, detected, up to s errors can be detected up to s errors can be detected if d minimum, write small letter d, up to uh, up to s errors can be detected per word if d minimum is greater than or equal to s plus 1. I will explain. Then similarly, up to t errors can be detected if d minimum is greater than or equal to 2t plus 1. Okay, this is the equation, that is d minimum we can calculate, then up to s errors can be detected if d minimum is greater than or equal to s plus 1, and up to t errors can be corrected if d minimum is greater than or equal to 2t plus 1. Then in this particular example we have uh, calculated that d minimum as 3. D minimum is 3. Therefore, substituting in this expression 3 greater than or equal to s plus 1, we can obtain that s is less than or equal to 2. Therefore, it means up to 2 errors can be detected using this particular code. Then, similarly, substituting that d minimum is equal to 3 here, then we obtain t is less than or equal to 1. That is, only a single error can be corrected using this particular code. This d minimum we have calculated, then the expression is up to s errors can be detected if d minimum is greater than or equal to s plus 1. Similarly, t errors can be corrected if d minimum is greater than or equal to 2t plus 1. For with d minimum equal to 3, we can say up to 2 errors can be detected, and up to one error, only one error can be corrected. Okay, we can stop now.